for the long absence of videos I had to study for the exams. In this video, we will learn about fractals, specifically fractal dimensions. What are fractals? Fractals are often self-similar shapes. One of them is the Sierpinski triangle, one of the most common fractals. It is also one of the most famous. It is created when you take a triangle and then take three other triangles and put them at the corners to create a triangle with a hole, repeating this process until you get the fractal. However, this is not the exact definitions of fractals. The true definition centers around fractal dimensions. We'll first take some four self-similar shapes, the first three of which are not even fractals: the line, a square, the cube, and the Sierpinski triangle. Each of these shapes is self-similar. A line can be divided into two smaller lines. Each piece is the same thing as the original part, just scaled down by 1/2, like this. Similarly, a square can be broken into 4 smaller squares. Each of those squares is scaled down by half compared to the original square. Likewise, a cube can be divided into 8 smaller cubes. Each cube has been shrunken in size by 1/2. And the core characteristic of the Sierpinski triangle is that if you scale down the whole thing by 1/2, it will be the exact same thing as the original copy, just with a mass of 1/4 the original triangle. We'll now imagine that these things are metal. For example, this is a thin wire, this is some metal sheet, this is a solid cube, and some kind of Sierpinski mesh. Now, notice that when we are cutting our line in half and scaling it down by 1/2, the mass goes down by, 1/2. Similarly, when we scale down the square by 1/2, the same square's mass is scaled down by 1/4. Which is equal to 1/2 squared. Similarly, the cube, if scaled down by 1/2, is really the same as the original cube, just scaled down by 1/2, with its mass scaled down by 1/8, which is 1/2 cube. Similarly, the Sierpinski triangle if scaled down by 1/2, is actually the same as the original triangle, just with the mass scaled down by 1/3. So it seems like there's nothing different. However, notice, every time we were with the line, the square, and the cube, it was always this integer power. For example, here the scaled down factor of the mass is 1, here it is 2, and here it is 3. In fact, if you notice, this number is actually the dimension of this line, square, or cube. For example, the line 1-dimensional and a square is 2-dimensional and a cube is 3-dimensional. So the dimension of our Sierpinski triangle is 1/2 to is equal is 1/3 equals to 1/2 the power of whatever dimension is, and thus we can ask what is 1/2 to the how 1/2 to the what power is equal to 1/3, which is exactly the same question as asking what is log base 2 of phi, because what is the exponent you would need to 2 to the power of what equals phi, and if you plug in log base 2 of phi, you would find log 2 of phi, you will find it is 1.585, almost 1.585, 1.58496. So this number here is actually the dimension of our Sierpinski triangle, and this is the concept of fractal dimensions. Sometimes the dimension of a certain shape is not not a whole number. It is instead any real number. Any real number dimension can be there. Another example is the von Koch snowflake. This is a snowflake which is a fractal. If you take one of the sections of it and zoom down, if you scale it down by 1/4, the mass will go down by 1/4. This is very similar, except this time the scaling factor is 1/4 and the mass goes down to 1/4, which is the same as asking 3 to the power of what equals 4. And if you plug in log base 3 of 4, it will be 1.2618. So this is the concept of fractal dimensions. Pause.